Hello, I welcome you all to this another interesting screencast. The problem reads that draw the shear and the moment diagrams for the beam, and this problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Right, so we have a simply supported rod here with this distributed force being governed by this function W naught divided by W naught times x squared divided by L squared. Right. So to start with, we'll need to find the equivalent force for this distributed load and also its location. All right. So let's call this location. Let's call this load as F FEQ, and then its location is from A is X. Okay, like so. All right. So we know that for us to find FEQ, we are going to use integration. So we are going to be moving from 0 to L, or integrating from 0 to L. The function itself, which is W, okay, dx, like so. Right, and then we've already been given the function, which is W naught x squared divided by L squared dx. Okay, so if we integrated this, it gives us W or x cubed divided by 3L squared. Okay, and we have our integration constant from 0 to L. Right, and this finally gives us W naught L divided by 3. Okay, is that so? That is it. So this is the equivalent force. Then its location X. Its location X is going to be equal to, okay, we need to use the centroidal equation, where we still use the equivalent force is the denominator, right? Okay, so we have W dx, x bar or x scaled W dx divided by from 0 to L W dx. This x scaled, this is the centroidal axis or centroidal location of the slice. Remember, when we are using this formula, we normally take a slice, right? Remember that we take a slice of the distributed loading, right? If we took this slice that we are going to call dx, imagine we call this dx, this slice, this infinitesimal slice, will have its own centroidal location. Remember this, right? And we'd call this as x curved, like so. Okay, so this is the one here. Okay, so basically what we're doing is we're just saying the moment, okay, forces divided by the summation of all forces should give us the centroidal location. Okay, so the summation of moments, all right, divided by the summation of all forces will give us the centroidal location. Okay, so that is what we are basically doing. So let's go ahead. So this gives us, since this point, when you look at this point x scaled, this x scaled will just be equal to x, all right, just equal to x. Okay, so therefore this is going to be equal to integral from 0 to L x w naught x squared divided by L squared dx, then divided by this. We already found it is the equivalent force, which is just W naught L over 3. Okay, we calculated this already. And then if we did the integration here and so on and everything, this will give us W naught x to the power 4 divided by 4L squared, okay, divided by W naught okay, from L to 0 there, I mean from 0 to L, and W naught L over 3. Alright, and then our x therefore is going to be equal to W naught x, I mean L squared divided by 4, then divided by W naught over 3. Okay, and then this finally gives us a 3L, right, a 3L divided by 4. So this is the location of this particular equivalent force. Right, okay, so with this information we should be able to move. Right, let's move on. So here we are. Let's now after finding all this, we need to find the support reactions. So at A, let me just get rid of this. So at A, we expect support reaction AY and then AX, and then at B we only have BY, right? And of course this is equal to, we said, WO divided by 3. So let's find what BY is. So summation of moments about point A and clockwise being our reference. What do we have? We have minus WOL divided by 3 times 3L over 4. And then plus BL times L equal to 0. Our BL is going to be equal to, of course, this 3 cancels out like so. So this gives us a W naught L divided by 4. Okay, and then let's have summation of forces in the Y like so. What do we have? We have AY plus BY minus W node L over 3 is equal to 0. We've already found what By is. So our Ay will be therefore equal to W or W node L divided by 3 minus By, which is W node L over 4. Alright, this therefore becomes equal to a 4W node L divided by 4 and minus a 3W node L divided by 4. So this is equal to W node L divided by 4. So we'll convert our By also to 3 W node L divided by 12, so that it is just represented with kind of same denominators. So By is equal to 3W node L divided by 12, and Ay is equal to W node L divided by 4. So we have the support reactions, and then we know that, of course, summation of forces in the x is just 0. That one is just 0. So summation of forces in the x direction, this is just equal to 0. I mean Ax is equal to 0, right? So we know this, so we can indicate this just equal to 0, like so. Alright, so now let's do a section. Okay, anywhere we have this load is continuous from A to B. We don't have any intermediate loads in between. Therefore, the section will only be done once. We only have one interval where we can do the section anywhere within the interval A to B. Okay, so it has to be between A to B. Okay, greater than A, less than B, anywhere within this interval. Alright, so let's do the section there. Okay, and let's call this point 1. So once we do so, we are going to have something like this. We have something like this. Okay, we have something like this. This point is A. This point is A, and it is equal to W node L divided by 12. And then we need, of course, the function for this load is W node x squared. Let me write it on top. W node x squared divided by L squared. Okay, but there will be also an equivalent force somewhere. Alright, and this equivalent force is this one here, because it's like we are just changing the integration constants instead of this one here. You've seen this one. Okay, instead of the constants being 0 to L, we just say 0 to x, so it remains this one, right? Is that fine? Okay, so instead of 0 to L, we just leave this the way it is. We just it's like we're changing the integration constants from 0 to x, so it remains this one. So that becomes the equivalent force. So that becomes our equivalent force W naught x cubed divided by 3 L squared. Right. So we need to find this location from there to there. Okay, I'll call this x. We need to find that. All right, so we are going to use the same criteria. So let me just look at how we found our x. So this x for this particular section is going to be equal to, because we are integrating from, so it will be w naught x cubed divided by 3l squared. We are integrating this from 0 to x divided by, no, sorry, this is supposed to be w naught x to the power 4 divided by 4l squared. Okay, we are integrating this from 0 to, it's just like this one here. See this one? This is what we are getting here. Okay, this one here. Okay, just the way we did for the first other case. The only thing that we just changed are the integration constants. Then w naught x cubed divided by 3l squared. Remember this? This is the part here, this part here, this part here. Okay, so once we have this, okay, these will just remain the way they are, where we have the x's, and then once we do the cancelling, this, okay, because this will remain the way it is, it will just be w naught x to the power 4 divided by 4l squared over w naught x cubed divided by 3l squared. So this and this goes, this and this will just remain with x, this and this goes. Therefore, what will remain with here is a 3x divided by 4. Okay, so this is going to be equal to, this x is equal to 3x. Let me write it somewhere. So this is equal to 3x divided by 4. So if I was to find this other distance here, this one here, so this was value of x that we are finding. So if we are to find this just becomes, because this distance here from there to there is x, right? So this one, let's call it x bar. Okay, all right. Then to find this other distance from the loading to the right, this will just be equal to x minus x bar, which is just basically equal to x over 4. Okay, this point is 1 here, so we expect a shear force V1 and the moment M1. Right, so the information is complete here. We are just going to apply the equations of equilibrium, right? So summation of moments about point 1 equal to 0, and clockwise being our reference. Alright, what do we have? We have the loading, which is w naught x cubed divided by 3l squared times x over 4. Okay, and then we have minus w naught l divided by 4 times x, and then plus m1 equal to 0. Therefore, our m1 is just going to be equal to m1 is equal to or minus w naught x to the power 4 divided by 12 L squared, then plus w naught Lx divided by 12. Alright, so this is about it, right? And then let's find the other one, summation of forces in the y direction equal to 0. Okay, what do we have? We have w naught x L divided by 12 minus w naught x cubed divided by 3L squared, okay, minus v1 equal to 0. Therefore, our v1 is just going to be equal to minus w naught x cubed divided by 3L squared plus w naught L divided by 12. Alright, so we have all the information that we need. We can now start doing the plotting. Let's draw these. We draw the loading there and everything. Okay, from there to there. Okay, there is fine, I think, and also there like so, and also there like so, something like this. Okay, so let me label the loading part, the loading diagram. A B, like so, and then we have this loading, this loading. Alright, it's loading like this. It's parabolic loading, right? Of course, it's w naught x squared divided by L squared. Of course, there we have w naught as the maximum, and then this point here we found our reaction at A equal to w naught L divided by 12, and then at B we found 3w naught L divided by 12. Okay, so we have the shear force diagram, we have the bending moment diagram. Can I move them a bit down? I think so, maybe just a bit down, maybe there, right here is better. Okay, like so. So let's go ahead. We have positive up, we have negative, we have 0, we have positive up, positive, negative, we have 0. Okay, alright, so now let's find the values at the boundary. Okay, so let's look at the values at the boundaries. What do we have? Alright, so we have v1, so v1 at x is equal to 0 from A. Okay, so where is our v1? Our v1 is here. This is our v1. Okay, So it is here. So when x is equal to 0 at A, V1 will be equal to W naught L divided by 12. And when V1, when x is equal to L, V1 is going to be equal to, let's plug it in. So V1 equal to minus W or X, that is L now, L cubed divided by 3L squared plus this L divided by 12. So this just becomes minus W L divided by 3 plus W naught L divided by 4. So this becomes a minus 4 W naught, right? W naught L divided by 12 plus W. So this finally just becomes equal to a minus 3WO divided by 2. So it becomes a minus 3W naught L divided by 12. Right. So we found these values when V1 is equal to, so let's find for moment also. Let's find for moment boundary values when so maybe I bring it down a little bit there. All right, so what is m1 when x is equal to 0, moving from A to B? Let me wrap this. We know that of course we know we have a hinge at A and the roll at B. We don't expect any moment because we don't have any support. We don't have any support moments. This is a simply supported beam. Therefore, when x is equal to 0, m1 at A is going to be equal to, where is the equation for m1? It is this one here. Okay, so this is just going to give us 0, right? And what is m1 when x is equal to L? We also expect a 0 at B. Okay, so when you plug in L in there, alright, it's supposed to give us 0, right? Okay, let me check it. M1 when L is equal to 0, when x is equal to L, so minus W naught, when this becomes x to the power 4 becomes L divided by L2, so we only have L squared divided by 12, then plus W naught L squared divided by 12. So this is equal to 0. So it is also 0. Great. We expected this. Alright, so we have this set of information. So with this information, we can now do the plot quickly. When we look at the functions, let's start with shear. Shear is a polynomial of degree 3. And we expect it to be curved, okay, like so. Okay, it's going to be curved like so. Right. So let's do the plots for shear. So shear at x is equal to 0 at A, we have a positive value of W naught L over 12. Okay, so let's say maybe this value comes up to here, okay, up to there. And then when x is equal to L, we have a value of minus 3 W naught L over 12, which is a little bit bigger than the other one. So let's put it maybe there, right? It's 3 times. Okay, something like so. Alright, this is curved. Just imagine this is curved. It cannot be better than this. It's curved. is curved and continuous until it hits that point like that. Alright, so this is what we have, and then we have this point here. We have this point here we've been told is W, or this point is W or L divided by 12, and then this point here is W or 3 W or L divided by 12. This is negative and this is positive. Alright, and then we have this point here. We need to find the length. We need to find the length from here to there. Okay, this information will be important to calculate the maximum moment. So at the point where shear becomes equal to 0, we'll have the maximum moment, because we know that dm dx, okay, gives us shear. Okay, and when shear, okay, when moment is maximum at that point, then we expect this derivative to be equal to 0, right? So this is where the principle comes from. All right. Okay, so we only have maximum either at this point. Okay, we have this kind of behavior at the point where the curve has a slope of 0, okay, which is at this point, okay, or minimum at that point, right? Great. So this is where the principle is coming from. So let's find that value, and for us to find that value, we need to just use the equation of shear. Okay, and then we have our shear equation as V1 equal to minus W naught x cubed divided by 3L squared plus W naught L over 12. So V1 we are saying is equal to 0. Therefore, we expect x cubed equal to x cubed equal to W naught L over 12 divided by W naught over 3L squared. So this and this goes. Alright, 3 there, 1, 3 there, 4. Okay, and then finally what we have is going to be equal to L cubed divided by 4. Okay, and then our x is going to be equal to L cubed divided by 4 to the power 1 over 3, which gives us what is 1/4 to the power 1 over 3. This gives us a 0.63. This is 0.63. This is 0.63 L. Alright, so this is 0.63 L. Alright, so now let's do the plot. So we expect this to be something like, okay, there we go. This looks better and a bit clean. So we have the maximum there where the slope is equal to 0. So let's calculate that maximum point. Let's call it M max. M max is going to be equal to, we are now using this left hand side of our shear, okay, from 0 to 0.63 L. So we integrate from 0 to 0.63 L, the shear function, which is minus W or W naught x cubed divided by 3L squared plus W naught L divided by 12 dx. Alright, so if we did the integration, this gives us minus W naught x to the power 4 divided by 12L squared plus W naught Lx divided by 12. Okay, and then we integration constant from 0 to 0.63 L. So if we did the calculation for this one, let's do that. So we have minus 0.63 to the power 4 divided by 12 plus what do we have? We have 0.63 divided by 4. Okay, so we have a 0.03937 W naught L squared. Okay, let's write it down. So this value here, this value is going to be equal to 0.03937 W naught L squared. Alright, and this moment is positive. Okay, I think that is about it. Let me just check through again this 1.63 to the power 4 divided by 12. Okay, that's a minus plus 0.63 divided by 12. Okay, sorry, I think that is about it, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, and continue sharing and subscribing to my channel. Bye bye, and see you in my next screencast.